All right, welcome back to Introduction to Speech Understanding. So, as you know, we have finished our section on automatic speech recognition. Last week we started talking about speech synthesis, and this week we're going to continue and really discuss the key theory behind speech synthesis, which is this idea of autoregressive signal generation. In particular, I'm going to teach you about something called linear predictive coding. And next week, then we'll talk about how to use the application programming interface for speech synthesizers in Python, and that'll be the end of the course. We only have one more week after this week, so please join me this week and then again next week. Let's see. Let's go to KCGI and let's go to Intro Speech Understanding, and let's find a Jupyter notebook. All right, so this week we're on Lecture 13. Let's open up Lecture 13 notebook. I'm going to kind of introduce speech synthesis this week using the idea of voice conversion. Suppose that you're speaking in your own voice and you want to somehow convert that to the voice of another speaker. You want to convert it from male to female or female to male, or you want to make your voice sound like a robot voice. All of those things can be done using a concept called linear predictive coding. So today I'll load some data and then I'll teach you about the idea of linear predictive coding, how we predict each sample of the signal given the preceding 12 samples. And then I'll show you how to synthesize speech using LPC. And then finally, I'll teach you how to turn your voice into a robot's voice. So first of all, let's just load a speech signal. Oh, I need to install Librosa. I have a new computer here, so I'd better install Librosa before I reinstall Librosa. So let me do pip install Librosa. There we go. Now that Librosa is installed, now I should be able to use it. Let's see. It's taking longer than usual. There we go. Let's play it and make sure that it loaded all right.
This is a speech waveform. これは音声波形です。
So this is again the same recording of my voice saying this is a speech waveform, これは音声波形です. And let's try to resynthesize this speech. So we'll go ahead and chop it up into frames. We'll use a frame length of 25 milliseconds. We'll use a frame skip of 10 milliseconds. And then we'll chop the entire file up into frames, and then we'll compute the magnitude short time Fourier transform and the spectrogram by taking the FFT and the absolute value and then taking its logarithm. And then let me plot the waveform and the spectrogram. And you can see the two parts of the waveform. Here's the English part. This is a speech waveform, これは音声波形です, with a silence in between. The spectrogram clearly shows every syllable. This is a speech waveform. And then korewa, the R in kore is very brief, somewhere around here, I think. Korewa on, and then this is the N in on, say, and then hake, des. So you can kind of see all of the different parts of the speech in the spectrogram and also somewhat in the waveform, although they're perhaps more clear in the spectrogram than they are in the waveform. So for example, when you say this is a speech waveform, the the R at the end causes F3 to come down, and the wave, the V causes the formant to come down, and so on. And that's very clear in the spectrogram. Let's look at the spectra at just 2.0 seconds, so in the wave of waveform, and then again at 2.3 seconds in the O of form. And let's just look at sort of what the signals look like in those two cases. So in wave, we see that the spectrum has it's an A sound. So the A has its first formant at 500 hertz, and its second formant is up around. Oh, in this case, it's much lower than expected. For wave, you would expect it to be up around 1500 or 2000, but here it seems to be around 1400 hertz. You can also see the pitch period. So in the waveform, you see the pitch period goes from here to here. Each of these is one glottal closure event. And so the pitch period is about 10 milliseconds, going from about 0.009 up to about 0.018, so maybe 9 milliseconds. And you can kind of see it in the spectrum as well. You can see here's the first harmonic, the second harmonic, the third harmonic. The fourth harmonic is right at the center of F1. The fifth, sixth, seventh harmonic, right? Here's the syllable form. And again, we can see the pitch is still around 9 milliseconds. And you can see the pitch frequency here on the first harmonic, second harmonic, third harmonic, and the F1, the first formant, is still around 500 hertz, but F2, the second formant, has dropped to below 1,000 hertz. So over here, it's at around 1,300 hertz or maybe even 1,200. Here, it's dropped to below 1,000 hertz because the O has a very low second formant. All right, all of that information we talked about last time. We saw how to model the resonances and how to synthesize a vowel by generating the pitch period with the excitation and then generating these formant frequencies using a resonator. But suppose we didn't want to try to synthesize all of the details of every transition here. Suppose instead we want to collect this information automatically from the speech signal and regenerate it based on information that the computer has collected for us. So we would like to be able to track F2 as it goes along here at about 2000 hertz in this is A, and then speech wave, right? In the speech, it drops down, and then in the wave, it comes back up again, and then in form, it drops all the way down. We would like to be able to collect that information directly from the signal rather than having to look it up in a book somewhere. And so one way to do that is to basically take these 4 formant resonators in a row and model them using a single 10th order recursion, right? Each one of these resonators looks back 2 samples. Each one of these is y of n is equal to e of n plus a1 times y of n minus 1 plus a2 times y of n minus 2. And since we have 4 of them in a row, that means that we need 8 feedback loops. We can add 2 more feedback loops just to be safe. So we'll take, say, S of n is equal to E of n minus the sum from k equals 1 to 10 of A of k times S of n minus k. So rather than just taking 2 feedback elements for the first resonator and then another 2 for the second resonator and another 2 for the third resonator, now we're going to take all 10 of them all at once. We'll just pass E of n, the excitation, into an order 10 resonator, and that order 10 resonator will produce the speech signal as the output. Now, we can actually find these 10 coefficients just using linear regression. This is the same as the statistical technique called linear regression. All we have to do is to try to predict what values of the previous speech samples will generate the current speech sample with the smallest possible error. And that method is called LPC, the LPC method in Librosa. Let's look it up. Librosa.lpc generates the linear prediction coefficients via Berg's method. So this is a particular computationally efficient algorithm that calculates those 10 coefficients. So I'm going to specify here that the order of the LPC filter is 10. And that means that that means that for every single frame, for each one of these frames, I want to find 10 feedback coefficients that will best approximate S of n as the sum of 10 previous speech samples. And I can actually look and see what the LPC coefficients are. So I'm going to here just create a figure that shows the speech signal in the syllable wave and the speech signal in the syllable form, and then I'll look at the LPC coefficients. The 0th LPC coefficient is always a 1. And then the others, A1 through A10, so A1, 2, 3, 4, 5, 6, 7, 8, 9, 10, those are all the coefficients that are necessary in order to reproduce S of n using a formula like this. Take E of n and then subtract S of n minus 1 times A1, S of n minus 2 times A2, and so on. So these are the coefficients, but it's not very informative just to look at them. It's kind of interesting. We can see that they alternate, right? So we can see that there's maybe more low frequency, more high frequency than low frequency, because it's going back and forth, back and forth. That suggests that there's a lot of high frequency information in this feedback. But other than that, we can't really tell very much by just looking at the coefficients. However, it turns out that we can take the Fourier transform of those coefficients in order to find out what the spectrum looks like. So the LPC coefficients by themselves are not very useful, but they can be used for many useful things. So for example, we can get the excitation signal. If we got the speech signal by subtracting previous speech samples from the excitation, then we can get the excitation by adding those previous samples to the speech signal. Or vice versa. If this one was a plus, then this one would be a minus. If this one is a minus, then this one is a plus. And so by Librosa LPC sets A of 0 equals to 1 for exactly this purpose. Right? We have S of n plus A of 1 times S of n minus 1 plus A of 2 times S of n minus 2. If A of 0 is equal to 1, then this is A of 0 times S of n. So we can do the sum from k equals 0 to 10 of A of k times S of n minus k. Right? So in a sense, what the Librosa.lpc does is it calculates the coefficients that are necessary to get rid of all of this extra vowel information and leave behind only the pitch excitation. So for every frame in the speech signal, for every sample in the frame, I'm going to calculate the excitation at that sample by taking, it'll just be zeros to start with, and then I'll take the kth coefficient multiplied by sample minus k, right? N minus k times A of k. Now I'm going to do that for every frame in the signal and for every sample in the excitation for k in the range from 0 to 10, right? K goes from in the range of 11, so that means starting at k equals 0 and going up to k equals 10. And by doing that, what I'm doing is I'm getting rid of all of the information that makes this a vowel, and I'm leaving behind only the part that makes this an excitation signal. And you can see here, here's the waveform, here's the word wave, here's the word form, and all of this is what makes it a vowel. This is the formant frequency, F1, ringing back and forth. And if we get rid of all of that, all that we have left behind are these pitch pulses. Once the glottis closes like this, right? And when the glottis closes, there's a huge negative pressure spike. Other than that, we just have random noise. So it's random noise, and then a huge negative pressure spike. And then more random noise, and then a huge negative pressure spike. So by using this equation, E of n is equal to the sum from k equals 0 to 10, A of k times S of n minus k, we get from the original speech signal, we can get back the excitation signal. All right, so two things. It's almost an impulse train. This is voice speech, so the excitation looks a lot like an impulse train. The other thing to notice is that different frames have different energy. The syllable wave is much louder than the syllable form, and you can see that in the excitation. The excitation here has an amplitude of 0.06, and the amplitude here is 0.01. It's much weaker in the second syllable than it is in the first syllable, a factor of 6 weaker. And so one of the important things that we get from this is the pitch period. This period is 10 milliseconds. The other important thing that we get is the gain, the average energy. We can take the sum of E squared of n and divide it by capital N, and then take the square root to get the gain. And really, that's all that we need. If we take that gain and divide it by the Fourier transform of these LPC coefficients, right? The speech signal we got by getting rid of the LPC coefficients. But if we take the Fourier transform of the LPC coefficients, that gives us a model of the spectrum. So I'll calculate the gain here by taking the square of the excitation in every frame, adding it over the samples within each frame, take the average, and then take the square root. This is called the root mean square. So I have the root of the mean of the square of the excitation. That gives me the gain in every frame. Let me print out then the size of the gain. Print, there are the size of the excitation is, and then we'll print excitation dot shape, and then let's print the size of the gain is, and then let's print the gain dot shape. And what you'll see is that when I'm adding over the samples within each frame, the shape of the excitation will just be the number of frames. So we'll have one gain in every frame. And then I'm going to create an LPC spectrogram, which will have that many frames and that many samples. And in each LPC spectrogram, I'll take 20 times the log base 10 of the gain, G here, divided by the absolute value of the FFT of the LPC coefficients. So I'll take these LPC coefficients, take their Fourier transform, and then I'll take 1 over that. Look at this. I'm taking 1 over the FFT of the LPC coefficients. And that will give us the spectrogram of the speech. So at the top here, I'm plotting the spectrogram of the speech calculated from the original speech signal. And at the bottom, I'm showing the spectrogram computed only from the LPC. Let me zoom these in a little bit more. Let me make this 14 by 8 maybe, so they're a little bit larger. You can see that the speech spectrogram contains horizontal stripes at the pitch period, right? This is the pitch frequency is 110 hertz. Here's 220, 330. Those are gone in the spectrogram. The spectrogram contains only the information about the vowel. It doesn't contain anything about the pitch, right? Here's the pitch information, and it's completely gone from the LPC. The LPC only tells you about which vowel it is. It doesn't tell you about what the pitch frequency is. Right? You can kind of see that here, right? There's no information about the pitch. We only have information about which vowel it is, although that information is kind of hidden here. Here it's very clear. The LPC only tells you about which vowel it is. It doesn't tell you about the pitch. And so we can use that information to resynthesize the speech with the original pitch or with a totally different pitch. We can take this excitation signal and pass it back through this equation, right, in order to resynthesize the speech signal. Or we could take a completely different excitation and resynthesize the same vowels, but with a different pitch. First of all, let me take these excitation frames and let me just add them all stack them all up. I'll use the horizontal stack command in NumPy to stack them all up into a row. There are 556 frames with a skip of 80 samples between each frame. So the total length of the speech signal is 556 times 800. Let's see, 500 times 80 should be about 4,000. So this is a little bit more than that. And now I'm going to synthesize the speech signal. Let me create a vector of zeros, which is the same length as the excitation. And for every sample in the excitation, I'll figure out which frame that is by dividing n over the frame skip. And then I'll set the synthesis signal equal to the input excitation minus a of k times synthesis of n minus k, right? So this is implementing exactly this equation. I'm saying S of n is equal to E of n minus the sum from k equals 1 to 10 of a of k times S of n minus k. And I'm using this excitation signal that I got from the original speech signal. I'm passing it back through that LPC filter in order to regenerate the speech synthesis. And the funny thing is, when I play this synthesis back to you, it will sound exactly like the original speech.
This is a speech waveform. これは音声波形です。
So you might think, oh, that's no big deal. That's the same speech. But it isn't. This is resynthesized from just that LPC.
This is a speech waveform. これは音声波形です。
If I go back to the original speech signal,
This is a speech waveform. これは音声波形です。
you see they sound exactly the same. All of the information in the original signal, all of this information, is included either here in the excitation or here in the LPC coefficients, right? And you can see that the excitation is mostly noise. So we could do a pretty good job resynthesizing this by just taking one pitch period, just taking one impulse every pitch period and passing it through the LPC synthesis. And so that's what I want to do next. First, let me generate the speech waveform and the spectrogram and the synthesized speech waveform and the synthesized spectrogram, and you can see that they look exactly the same. That's really useful. That's how your cell phone works. A cell phone basically takes the speech waveform and chops it up into excitation and LPC coefficients, right? But that's not very much fun. If we want to have fun, let's turn it into robot speech. And the way that we can turn it into robot speech is to create an excitation signal, which is just a 1 once every 10 samples. So let me say I want 100 hertz. I'm going to generate a pitch that's exactly 100 hertz pitch, and I'm going to make the excitation signal just be one impulse once every once every 10 milliseconds, right? Fs over 100 should be 10 milliseconds. And then I'll say that the excitation is equal to the gain times that pitch pulse, and the speech is equal to that excitation. And then from that speech, I'll subtract A of k times S of n minus k. So I'm just going to create this very artificial excitation, but I'll produce all exactly the same vowels.
This is a speech waveform. これは音声波形です。
So you see we've got exactly the same vowels, but now instead of the original pitch, now I have this artificial pitch created using this line. Just once every 10 milliseconds, I've got one impulse once every 10 milliseconds. Let's try to plot that actually. Let me add a window here and let's do fig is equal to plot figure, fig size equals, let's say 14.4, layout equals tight, and axis we'll say is fig.subplots1. We'll just have one subplot and we'll plot, let's choose just a few of these. Let's see, this is around what sample number? It's excitation 200, so 200 times 80. Let's plot P of 200 times 80 up to 201 times 80. That should be one frame of the pitch signal, and let's see. Oh, that didn't show us anything very interesting, did it? Oh, 200 times 80. Let's see if that's interesting. That's still not very interesting, so let's go up to 200. Let's do 5 frames in a row. And now we can see, right, the pitch excitation now is just 5 impulses, right? It's just the most boring possible excitation, and that's why the robot voice sounds like it does.
This is a speech waveform. これは音声波形です。
Let's look at the E robot. The excitation of the robot is that pitch signal multiplied by the gain. And so you can see that it changes as we go into the syllable wave. The pitch gets louder as we go into the syllable wave and then gets quieter again as we come out. Let's look at the synthesized speech waveform. It should have all of the vowels in it, but with varying amplitude. And so here you can see the syllable wave being produced by passing that excitation, E robot, through the LPC synthesis filter. And the result sounds like intelligible speech, but it sounds like a robot.
This is a speech waveform. これは音声波形です。
This is kind of cool, actually. This is the nice thing about this is that we can change it in whatever we want. So for example, we can make it sound female by just changing the pitch from 100 hertz to 200 hertz. Once every 5 milliseconds, let me create an impulse.
This is a speech waveform. これは音声波形です。
So you can see that we've generated we've simply done twice as many pitch pulses. Let me plot that as well. Let's see. If we plot that, you can see that the difference between these two is that the female robot has twice as many pitch pulses. Right? The male robot has a pitch pulse once every 10 milliseconds. The female robot has a pitch pulse once every 5 milliseconds. So twice as many. Let's see, it should have one here, one here, one here, and then this is F1 ringing in between. So all we had to do to make it sound female was to double the pitch frequency. We can also do things like make F0 go up toward the middle and then go down toward the end. So let me say that F0 is 200 plus 40 times t, that's a straight line going up, or 400 minus 40 times t, that's a straight line going down. And I'll choose the minimum of those two so that F0 goes up and then comes down again. T0 is the pitch period in samples, so that's the sampling rate, Fs, divided by the pitch frequency, F0. So you see it, F0 goes up and then down again, T0 goes down and then up again. Now let me create a robot excitation, which is equal to the gain of that frame. Oh, and then every time I'm going to add the current pitch period of that frame. So while, I'll take the sample number, the sample will start at 0 and then go up to the length of the excitation. And every sample, I'll figure out which frame it is and use that gain accordingly. And then I'll skip over T0 samples in between in order to make sure that that I only change that all of them are zeros. All of them are zeros except for once every pitch period. And when I do that, I should get a waveform where the gain changes as we change different syllables, and the pitch is, we have a lower pitch frequency, so a longer pitch period here in the word wave. In the word form, notice that the pitch period is shorter, meaning that the pitch frequency is higher. And so if we play that, we get something that sounds like this.
This is a speech waveform. これは音声波形です。
So you can see the pitch goes up and then it goes down. The pitch period goes down and then it goes up. And so we can play around like that. In this way, you can easily generate robot voices, or you can generate any pitch frequency you want. If it's in Chinese, you can change the meaning of the word. If it's in English, you can change the grouping of syllables to make it sound like almost anything you want. For the homework, let's do those three parts. So let me open up the homework. So for the homework, we'll have three methods. One will be just LPC to perform linear predictive analysis using Librosa. Second will be synthesize, and the third will be to generate a robot voice. So let's see, in LPC, what I want to do is I want to take in the speech waveform and the frame length in samples and the frame skip in samples and the order of the LPC. And so first of all, I just want to chop it into frames, right? So first of all, I want to create frames is equal to NumPy array of speech from M to M plus frame length for M in the range from 0 up to length of speech minus the frame length with a skip of frame skip. So we'll create one frame once every frame length. Once every frame skip, we'll create a new frame, and each frame will be frame length long. All right, and now I want to find the LPC coefficients. So A is equal to Librosa LPC of the frames, and I think that's all I need, right? Axis along which to compute the coefficients. So axis is equal to -1 by default, so that should be all I need, I think. And then I want to find the excitation. The excitation is the linear predictive excitation in frames. So that should be the same size as the original frames. Oh, no, it should be, yeah, n frames by frame length. Okay, so the same size as the original frames. Let me just figure out what n frames and frame length are. Those are frames.shape. Oh, I already had frame length, didn't I? That's all right. And then I want to find for each frame in n frames, for each sample in frame length, and only the last frame skip samples in each frame need to be valid. So if I start out with not invalid samples, that's fine. So I'll just say, actually, let's just start from the order. Oh, I needed to specify the order here too, didn't I? Is that how that's done? Order equals order, axis equals -1. And let's go ahead and specify the axis as well. And so we'll start out with sample number order so that we can go set each sample of the excitation. Equal to the input speech signal. And then we want to, for k in the range up of 1 to order, we want to subtract from excitation of frame and sample number. We want to subtract A of frame k times frames of frame sample minus k. So we want to take the excitation and set it equal to the input speech signal minus the LPC coefficient multiplied by the delayed frame. No, actually, I want to add because that's right. Subtraction was synthesis and adding. Let's just check that to make sure. Subtraction was synthesis, so adding is equal to getting the excitation back again. Yeah, so I add to get the excitation back again. Here I just added even from sample 0. I could do that too, but let's take the excitation as equal to the frame, and then we'll add to that from range 1 to order +1, we'll add the previous frame. And then let's just return A and excitation. I think this will be correct. Let's find out. This is a little bit different from what we did in the notebook, but let's find out. So if we run the docstring, if we run the excitation analysis, oh, and we wound up with too many values to unpack, expected 2. Frames.shape has more than 2. Oh, right, because this should be just like that. Because here I have a vector, and then I want each of those vectors to be one row in this matrix. Let's see if it was the correct debugging. Frame length is not defined. There we go. Just debugging as I go here. There we go. Now we have the spectrogram and the LPC spectrogram. So that should be valid. Now let's resynthesize. We were given an excitation signal. We want to resynthesize, and the LPC coefficients and the frame skip, we want to resynthesize the speech signal from its coefficients. So we'll take in the excitation signal with a length equal to the total duration, and we're given the coefficients A. So we want this output speech signal to be zeros with a length equal to the length of the excitation. And then for every sample in the synthesis, we want that sample to be the excitation sample corresponding. And then we want the frame index to be the integer of n divided by the frame skip. And then we want for k in the range from, oh, let's find out what the order is. And this is actually not the order, it's the order plus the size of A is the order plus one, right? Because if we had 10 coefficients, then A has 11 columns. So that's fine. We're going to go from K in the range from 1 up to the order plus 1, right? So it'll actually go from 1 to 10. We want to say that synthesis of N plus equals, no, minus equals. We did plus up here for the analysis, so we want to do minus down here for the synthesis. Minus equals A of frame, comma, N modulo frame skip, right? I want to divide, I want N modulo frame skip, I think. Oh no, A is just K. Yeah, that's right. I want the kth coefficient, and I want to multiply that times synthesis of N minus K. I have synthesis of N is equal to the excitation of N minus frame A of frame comma K times synthesis N minus K. That looks about right. Let's return that synthesized signal and see if that gives us the signal that we want. Excitation was not defined. Oh, because I called it E. I think that's the only place that's used.
This is a speech waveform. これは音声波形です。
Great, so we're able to resynthesize the speech signal exactly as it was to begin with by taking this excitation. The excitation is just the last frame skip samples from every sample of the excitation that we generated in the analysis. So we'll take this natural excitation, and that natural excitation will stack it up into a signal, and then pass it through the LPC synthesizer in order to get the speech back again. That's very useful if you're designing cell phones, but it's not very much fun. So let's do something fun by creating a robot voice. The robot voice will take in an excitation, which is the original speech signal, and it'll take in a pitch period, and it'll take in the frame skip. And from that, we want to return the gain for each frame, right? So we want to calculate how loud each frame is. And then we want to generate the excitation for the robot voice, which is the pitch period for the entire signal, 10 milliseconds for the entire signal or whatever, um, scaled by the gain for each sample. All right, let's try that. Let's see. We have the robot voice. We want to delete this runtime error. And then we want to calculate the gain. That should be just the square root of the sum of the square of the excitation. And we want to sum it along the second axis, that is along the samples within every frame, and then take its square root. That gives us the gain in every frame. The number of frames should just be the length of the gain vector now. However many samples there are in the gain, that's the total number of frames. And now we want to generate a robot excitation. So the pitch, P, just the pitch signal, is just all zeros. And that'll be zeros of, let's see, what will be the length? That'll be the number of frames times the frame skip. That'll be the length. And then that robot pitch, once every T0 samples, we want it to be a 1. Either a 1 or a -1. It doesn't really matter very much which direction we go. Now we want E robot to be equal to P robot. But now we want to take every sample and scale it by the corresponding gain. So for n in the range for up to the length of E robot, we want E robot to be multiplied by the corresponding gain. And by corresponding, I mean which frame number is it? So we want the sample number divided by the frame skip. right? That tells us which gain we want to multiply that sample of eRobot by. So eRobot of n gets multiplied by the gain of the integer of n divided by frame skip. That gives us the robot excitation, and then we'll pass that robot excitation into our synthesizer to get back again the robot voice. So for now, we're just going to return the gain and the robot excitation. So in that way, we've created this artificial excitation, which has just a constant pitch period at whatever pitch period we choose, scaled by the corresponding gain from every frame. All right, let's try that in the notebook and see how well that works. All right, here what have I done? eRobot is equal to pRobot. It's a NumPy ND array. Maybe I shouldn't have those be separate files. Maybe I should just take this and call it eRobot to begin with. And then now I've got eRobot has one pitch period, one once every pitch period. And now I'm going to scale each of those. I'm going to scale eRobot of n, let's say, is equal to eRobot of n times the gain of, oh, I see the problem. I used curved parenthesis here instead of square brackets. Gain is not a function, gain is an array. So I want eRobot of n multiplied by gain of integer n over frame skip. So the thing about getting rid of pRobot was not necessary, but it also shouldn't hurt. Let's try that.
This is a speech waveform. これは音声波形です。
There we go. So that worked all right. Let's see. It looks like maybe one of the grading functions is not working. Oh, we've got two of them failing, but the failure is just that it has 556 rows instead of 557. That's acceptable. So if your error is just 557 instead of 556 rows, don't worry about that. Go ahead and submit anyway. Now that we've got that code, let's go ahead and open up GitHub Desktop and check in our results. Homework 13 is done. And push it to the origin. And then let's check GitHub to make sure that that got checked in okay. Let me switch from my teacher to my student account. And in the student account, if I check on lecture 13, there's the LPC code, there's the synthesizer code, and there's the robot voice code. So if I take this URL and go over to Canvas, homework 13, I should be able to enter the copy of your enter the URL of your copy of homework3.py, and if you enter your URL here, then I will be able to grade it before next week, and you should be able to get your grade right away. That's all for this week. Let me go ahead and stop recording, and then we can take attendance.